Good afternoon. Today I'm going to talk to you about a new method for measuring higher order gravitational lensing effects that cause galaxies to look like bananas. This is a hybrid analytic image modeling and image moments approach to gravitational lensing. For our first order of business, we need to discuss the idea of gravitational lensing. We see an object because light leaving that object hits our eyes. And if that light travels in a straight path, then what we see is what the object actually looks like. If that light travels on a curved path, though, the image of the object we see is distorted. Distortions can be magnification, for example. This is what happens when you look through reading glasses. The light gets bent by the lens, and the object you're looking at appears larger. It turns out that anything that bends light acts as a lens. And from general relativity, we know that matter bends space-time and light travels on bent space-time. So consider this diagram here. Over on the right is us, and on the left are some source galaxies that we are observing. In between us is a large, massive galaxy cluster with dark matter. As the light leaving a source galaxy passes by this large cluster, it gets bent, which means that this cluster acts as a lens. If the size of this cluster between us and a galaxy we wish to observe is small, we can make the so-called thin lens approximation. Here, the more complicated curved lines that light follows as described by general relativity can be turned into a few straight lines with kinks at the location of the lens, just as we do in undergraduate optics. Gravitational lensing is a game of two-dimensional planes, and there's two of them. Each plane is described by a two-dimensional coordinate. On the lensing plane, which is the plane that we actually see, that coordinate is theta, and on the source plane, that coordinate is beta. And since the source plane is the background galaxy, think background and beta, both start with B, as a mnemonic to remember which coordinate is which. These coordinates differ by a deflection angle, which we can understand as the gradient of the lensing potential. The lensing potential is the two-dimensional analog of the Newtonian gravitational potential integrated along the line of sight. So here we begin to see how gravitational lensing is a probe of the underlying matter distribution. So what happens when we start taking derivatives of this potential? We get lensing effects. The first of which is known as convergence. One of the definitions of convergence is the dimensionless ratio of projected surface mass density of the lens, sigma, to the critical surface mass density, sigma critical, which depends on the redshift of the source and the lens. So kappa is therefore directly related to the matter distribution of the lens. And this is the point of gravitational lensing. We don't actually care so much about the thing being lensed so much as the thing doing the lensing. Gravitational lensing is a cosmological and astrophysical probe that allows us to determine matter distributions, dark and baryonic, of clusters and of large-scale structure. Getting back to convergence itself, we can further understand it as a lensing effect. The formalism for lensing effects is as follows. We define a two-dimensional complex gradient operator where the subscript 1 denotes the x-axis and the subscript 2 denotes the y-axis. In terms of lensing, the convergence is related to the second derivative of the lensing potential. To see what the convergent field looks like, I've created a figure using a code I wrote called lenser, which will be the subject of the rest of this talk after we finish discussing this formalism. If we take an unlensed circularly Gaussian galaxy in the background plane and apply some convergence, the result is that the galaxy is magnified. And this is completely symmetric, so convergence is an isotropic lensing effect. The convergence is also useful in that it defines the difference between weak lensing and strong lensing. Weak lensing is defined by kappa is much less than 1. And weak lensing is the regime we will be operating in for the rest of this discussion. Now, since the gradient operator is complex, there's a second way that we can take the second derivative, which leads to an anisotropic lensing effect known as shear. Shear is typically used when studying weak lensing. This figure shows what shear looks like when applied to that same unlensed Gaussian galaxy from before. Unlike convergence, shear is a vector, which means it has two components, which are both shown here. And shear stretches the original galaxy. You might ask yourself the following question. Aren't there elliptical galaxies that would look like this without lensing? How do I know if an oval is the result of shear or if the galaxy just looks like an oval because it has some type of intrinsic ellipticity? And the answer to that is you don't. You can't know. And this is known as the shear ellipticity degeneracy. An image of a single galaxy is not enough to determine how much shear is present. So shear is therefore used on large scales. One assumes some amount of intrinsic source ellipticity, observes an ensemble of galaxies in a field, and looks for a coherent alignment of these ellipticities. If all of the oval-shaped galaxies point in the same direction, that indicates the presence of a shear field. In terms of the lensing potential, we can write the shear like this. Now, if the convergence and shear are effectively constant within a source galaxy image, which is the typical assumption, then this would be the end of the story. The fact is that shear and convergence are not constant within an image, and so we have higher order lensing effects. Flexion. First flexion is the result of the first of two ways we can take the third derivative of the lensing potential. And first flexion appears as a centroid shift. Being a higher order term, flexion is more sensitive to smaller scales than is shear. The strength of the signal falls away from the halo faster than the shear does, and as such, flexion acts as a sort of high-pass filter for density. What's more, unlike shear, flexion is local. It is the gradient of the convergence. So measuring the flexion of an object gives you the gradient of the convergence at that object, whereas shear is not related locally to the density. There's more to this story because there's another third derivative we can take. The second flexion is the derivative of the shear. We will not be concerned with second flexion in and of itself for this study, but it is important to include it because when we take an unlensed galaxy, add some shear, add some first flexion, and add some second flexion, we get the banana looking distortion that can be observed and understood as a flexed object. Despite the promise of useful results from flexion, the flexion signal is very difficult to measure. Previous attempts at measuring flexion include decomposing images into shapelet basis sets, a method derived by Goldberg and Bacon, both of whom have graced us with their presence here today. Shapelets takes advantage of the very well-known math of the quantum simple harmonic oscillator. Other attempts have been an image moment analysis developed by Okura and subsequently by Goldberg and Leonard. The newest of these approaches is a forward modeling, parameterized ray tracing known as analytic image modeling. or AIM, which is developed by King. We're going to discuss the latter two techniques. First, let's take a look at image moment analysis. This integral allows us to calculate the unweighted moments of the surface brightness in an image of a galaxy. And it turns out that flexion is related to the octopole and hexadecapole moments, that is the third and fourth order moments. This zeta, delta, and psi term are known as holics, the higher order lensing image characteristics, which were first written down by Okura. The basic idea here is that since it's already established that shear and ellipticity are related to quadrupole moments or second order, then flexion must be related to the third order moments. And since the galaxy in the source plane is unobservable, the method simply calculates flexion in the lensing plane without so much concern for what it looked like in the unobservable source plane. So what are the pros and cons of the image moment analysis approach? Well, they're easy to code. The code runs very quickly, and they provide estimates for the flexion, which is the thing that we're after here. Sounds great, but what are the cons? Well, they provide estimates for the flexion. They are particularly sensitive to noise, the window functions, and they also have a very complicated point spread function, PSF, deconvolution. The other method, analytic image modeling, takes advantage of the fact that gravitational lensing conserves surface brightness. So we can directly relate an observed surface brightness distribution in the lens plane to a distribution in the source plane. The idea of this method is that while the source plane is unobservable, we do know what galaxies are supposed to look like. We can write down a functional form of the surface brightness of a galaxy as a function of radial distance. We employ a modified Sersic intensity profile for the galaxies, where theta prime is the radial coordinate, theta s is the characteristic radius, and ns is the Sersic index, which controls the steepness of the profile. Theta prime can be written like this. X and Y are your centroid subtracted source plane coordinates, rotated by some orientation angle phi, where Q is the semi-major to semi-minor axis ratio for the galaxy. We then relate the unlensed and lensed coordinates, beta and theta, by Taylor expansion. And all of the parameters here comprise a 13 parameter space. Now we have to remember, though, that we need to deal with the shear ellipticity degeneracy. And to do this, we set the shear-like terms equal to 0, allow the ellipticity parameters Q and phi to absorb the shear, and remove the shear from our parameter space. We then do a chi-squared minimization over this parameter space. So what we're doing here is the following. We guess a model for what the galaxy would look like in the source plane, guess some amount of flexion that gets us to the lensing plane, and see if our model of a lensed galaxy matches the actual lensed galaxy image using chi-squared as the figure of merit. So what are the pros and cons of this method? The pros are that it's highly robust. Because the AIM method's based on model optimization, covariance analysis can be done on the parameter space. And due to the fact that AIM is a forward modeling approach, PSF correction can readily be applied during parameter minimization. So we can actually convolve the model image with the PSF rather than attempting to deconvolve the real image. What about the cons? Well, potentially has a very large degenerate parameter space, which is bad news for chi-squared minimization. If there are too many parameters, it won't properly minimize. It's also susceptible to getting trapped in bad local minima of the chi-squared surface. So here's where I come in. I try to address the problems in these models. First, I make some improvements on AIM by reducing the size of its parameter space. And I also expand upon the image moments approach by using image moments to compute estimates for all of the parameters we just discussed. That is, I use image moments as an initial guess for the AIM parameter space. I compute initial estimates for the centroid, Q and phi by relating them to the complex ellipticity. I relate the Sersic index and the characteristic radius to each other and to Q and the quadrupole moments, which means that NS and theta S are initially coupled, which we'll get to later. And we compute the flexion using the image moments Holix approach. Then with these initial guesses in place, I employ AIM in order to fully minimize the parameter space. So the benefits of this hybrid model are that every parameter has an initial guess. These initial guesses prevent AIM from wandering into bad local minima of the chi-squared surface. It's more accurate than simply using image moments as estimators, especially for flexion. And since good initial guesses are provided, it converges to a minimum faster than AIM would alone. I wrote this code called Lenser, which is a fast, open source, minimal dependency Python tool that is able to measure flexion. Lenser is an implementation of the hybrid model I just described. So here's the pipeline of the Lenser code. We have two flowcharts here of varying complexity. Let's take a look at the one on the left first. Remember what we're looking to do here. We're interested in measuring flexion in a galaxy image. So Lenser takes as an input an image of a galaxy in the form of a FITS file. Lenser also accepts noise maps, segmentation maps that may have been generated using source extractor, PSF. And then once an image is imported, Lenser cleans it up. It estimates and subtracts the background. It computes a noise map for you if one's not provided. And it then proceeds to generate an elliptical mask around the galaxy so you can exclude any extraneous light sources near the edge of an image. Lenser then gets an initial guess from the image moments and proceeds to a two-step chi-squared minimization. And I mentioned earlier that NS and theta S are coupled initially. So the first step is to decouple them. And the final step is to do a local minimization over the entire parameter space. And at each iteration, the model image is convolved with the PSF, if one is provided for proper comparison to the real image. And Lenser then exports the image of the model galaxy along with numbers for the flexion. The flowchart on the right takes a slightly less sophisticated view of the pipeline. Picture of a galaxy goes in, fax machine noises, picture of a galaxy comes out, which is the model, and it'll spit some numbers out at you. So what is the first thing you do when you write a piece of software? Got to make sure it works. And because Lenser forward models, you can actually use it to test itself. So here I use Lenser to simulate a galaxy with random shape and lensing parameters. I then export it to a FITS file and clear the memory in Lenser. Which means that when I import the image back into Lenser, Lenser has no knowledge of the parameter space that it just used to create the image. On the left panel, we have that simulated image. In the middle, we have Lenser's model of that image, and on the right, we have the difference between the two. You'll notice that I'm using the same grayscale limits so I can compare the residual with the original galaxy in the model. So looking at the residual plot, which looks like a perfect subtraction, looking at the chi-squared of 1.02 and inspecting this table of values comparing the input to reconstructed parameters, we can conclude that Lenser is robustly able to fit itself, and so is able to successfully measure flexion in an image. If this seems a little too much like shaking your hand with your other hand and saying, well done, I can't say that I blame you. You should use an independent pipeline to make sure that your thing works. And luckily, a colleague of mine, Jacob Spies, developed a software tool that produces images of lensed galaxies with first and second order lensing effects using multi-dark n-body simulation data. Jacob will have knowledge of the lensing fields of any image he creates. And as a test of Lenser, Jacob created 100 images of lensed galaxies. He then handed those images off to our undergraduate, Jake Delano, who then fed them through Lenser. And Jake reported back with the flexion values that Lenser measured. In this plot, we see the Lenser output of first flexion versus the correct first flexion values. And the blue and the orange indicate the x and y components of first flexion. And Jacob computed correlation coefficients of 0.973 and 0.987, respectively. And at this point, we were satisfied that the Lenser tool was working properly to a reasonable enough degree. As you might guess, the next logical step is to use Lenser to measure the flexion in images of real galaxies, rather than just simulated ones. But before we get to that, I want to mention one additional thing you can do with Lenser: a covariance analysis of the parameter space. So here you see a triangle plot of the forecast marginalized constraints. What I did here was simulate an ensemble of 1,000 galaxy images. These images are copies of each other. They have the exact same parameter space in each, except for the centroid, which I dither within 1 pixel. But they also have the same flat noise map added to them. The only difference between these images is the randomization on top of the noise maps. And the goal here is to measure Lenser's response to noise. So feeding these 1,000 images through Lenser, we take the 1,000 sets of reconstructed parameters and compute the covariance matrix. I'll repeat this process for a flat noise map that is twice the one that I just did. And we get 2 sets of 1,000 images, and so 2 covariance matrices, and those are the black and gray error ellipses on this plot. So first of all, just looking at one covariance matrix at a time, we see things right away that we should expect. Remember that correlation between parameters should look like an ellipse that is stretched and oriented at an angle of 45 degrees relative to the positive x-axis. So for example, we see that these 2 terms, psi111 and psi122, which together make up the x component of first flexion, are correlated. Whereas something like this, which is cross terms between f and g, are anti-correlated. The ellipse points the other way, which we would expect. We also see that ns and theta s are anti-correlated, which makes sense since steepness and size are going to be inversely related. The main takeaway of this plot, though, is the comparison between the 2 covariance matrices that are overlaid. And we see that reducing the noise by a factor of 2 reduces the error on the flexion by a factor of 2. So what we forecast here is that flexion-based studies would greatly benefit from future surveys that are going to take higher quality images of galaxies. So now for some real galaxy images. Here I'll be presenting some results from a paper written by my colleague Joseph Fabricius, myself, and Dave Goldberg, submitted for publication to monthly notices. As part of Joseph's thesis work, he wanted to study how shape, color, and distance of galaxies affect measurement of flexion. There's this as of yet untested assumption in the flexion community that elliptical galaxies are ideal targets for flexion studies, and this study in part addresses that assumption. To do so, we used Lenser in order to analyze 2 catalogues, one low redshift, one high redshift, that contain images of galaxies along with information about their known morphological types. The first catalog is F and G, which is the low redshift one. The galaxies have redshifts ranging from 0.001 to 0.05. There are 4,458 galaxies in this catalog, and the images are taken from the Sloan Digital Sky Survey, DR4. The high redshift catalog is Cosmos, which has galaxies varying in redshift from 0.15 all the way up to 8. There are 1,492 galaxies. These images are taken from Hubble Space Telescope, and this catalog is actually from the CANDLES program that's looking in the cosmos field. Here we see a galaxy image from the F&G catalog and an image from the Cosmos catalog run through Lenser. And as before, with the simulated image, left to right is the real image, the model, and the residual. And if you're wondering at this point, what are the X and Y axes and why are they different for each image? They're pixel numbers. And F&G and Cosmos just have different size images. So let's address the title of our paper. Why would shape, color, or distance affect flexion measurement? The answer is something called intrinsic flexion, which is a non-lensing flexion signal. What is a non-lensing flexion signal? Well, remember that first flexion manifests as a centroid shift. So any non-lensing effect that causes an apparent centroid shift would be measured as first flexion, even if there are no lensing fields present. So this intrinsic flexion is therefore a noise associated with the measured flexion signal. And this has been a serious challenge for flexion studies. So back to the assumption that I mentioned, it's expected that early type or elliptical galaxies should be more well-behaved in a measure of intrinsic flexion, as the galaxy profiles are less likely to contain artifacts like spiral arms to distort the flexion measurement. Here's a result of testing that assumption against these two galaxy catalogs. We see the low redshift F&G catalog on the left and the high redshift Cosmos catalog on the right. All four of these plots are histograms of a quantity referred to as A times F. A is the size of a given galaxy, and F is the first flexion. And it turns out that A times F is scale invariant. So this is to say that the same apparent galaxy image produced at different distances will have the same combination of AF. This becomes a very good measure of the intrinsic flexion in a distribution of galaxies. The scatter, when you're looking at an ensemble of these, sigma AF is the measure of the noise in measured flexion for an object of a given size. There's two ways to quantify whether a galaxy is early type or late type. First, we have morphological information from the F&G and Cosmos catalogs. And second, we can use the Sersic index. And canonically, n equals 1 for late type or spiral galaxies, and n equals 4 for early type or elliptical. But there is a good amount of variability between those. The plots on the left cut the distributions into low and high Sersic index, and the plots on the right separate the galaxies by their early type or late type morphologies. And we see that since morphology and NS are closely related, the bottom plots closely resemble the top plots. All four of these plots point towards the same result. Early type galaxies have a smaller scatter and intrinsic flexion, and late type galaxies have a larger scatter. And therefore, elliptical galaxies have less intrinsic flexion noise and are better for flexion studies, as expected. So to summarize, gravitational lensing is a cosmological and astrophysical probe of matter distributions. Weak lensing measurements are typically done with shear. However, flexion, which is a more sensitive probe to small scales, and shear allows us to extract information from lensing surveys that are traditionally left behind. I wrote a code called Lenser, which is a robust analysis tool for measuring flexion. Using Lenser, we find in Joseph's work that early type galaxies have the smallest noise attributed to unlensed shape information. And furthermore, by choosing galaxies with early type characteristics, Joseph finds that we can reduce intrinsic Flexion noise by a factor of 2. So as for my future plans after this project, I plan to study cosmic Flexion, the analog to cosmic shear, because I believe that this may be a powerful probe that is uniquely sensitive to modified gravity theories on intermediate scales. I'd like to first and foremost thank Dr. Dave Goldberg for his stewardship, his constant advice and support. I'd like to thank Joseph Fabritius for eagerly letting a first-year grad student contribute to his very interesting work. I want to thank the Lenser test crew, Jacob Spies and Jake Delano, and I want to thank Dr. Dave Bacon for advice and encouragement on the front of cosmic Flexion. And I want to thank all of you for joining.